This is a pre-recorded talk for Prox 2020 on the paper Parametrized Metrical Task System, which is joint work with Sebastian Bubik from Microsoft Research AI, and I'm obviously the other author. So what are metrical task systems? It's a fairly general model of online computing that captures many more specific online problems. In this setting, there is a single server that moves in an endpoint metric space, which we denote by M with point set X and distance function D. Starting from an initial state S0, that is one of the points in the metric space. The server is given a sequence of requests, row 1, row 2, and so forth. Each request assigns a service cost to each of the points in the metric space. This is either a non-negative real number or infinity, which means that this state is excluded from serving the request. In response to a request sequence, the server moves through points in the metric space. So S1 is the location after receiving the first request, S2 is the location after receiving the second request, and so forth. And the server has to pay the cost of moving. So for every request, the server pays the cost of moving from the previous state Si-1 to the current state Si. And after moving, it pays the current service cost at the state that it ends up in. So this is the general problem. And the general question, of course, is to design online algorithms that serve the request sequence without knowing the entire sequence in advance, just responding to the current request. As usual, we're interested in the competitive ratio, which is roughly the ratio between the worst case overall sequences of the ratio between the server's cost, the online algorithm's cost, and the optimal cost of serving the entire request sequence, knowing all of it in advance. And more specifically, we'll be interested in the competitive ratio of the best possible algorithm in particular settings. So what's known about this in general? The model was introduced in a paper by Borden, Lineal, and Sachs. And they showed type bounds for the deterministic competitive ratio. So in every endpoint metric space, the competitive ratio, the best competitive ratio is exactly 2n-1. More recently, bounds on the randomized competitive ratio. So when the algorithm is randomized, you look at the expected cost versus the optimal cost. That's randomization against the oblivious adversary, and I won't go into the specifics of these details, but it's sort of the natural way to think of randomized algorithms. So randomization in online algorithms often helps, and this is the case with metrical task systems. Very recently, Bubik et al. Showed that the randomized competitive ratio is at most order log square n on an endpoint metric space, any endpoint metric space. This improves previous results based on other methods. And earlier, the randomized, there was a lower bound on the randomized competitive ratio established by papers of Bartal et al. of omega log n over log log n. So in the randomized case, there is a bit of a gap here. It's interesting that both the upper bound and the lower bound are based on what are known to be type bounds for hierarchically separated trees of theta of log n. What's a hierarchically separated tree? Again, informally, one level hierarchically separated tree is just a uniform metric space. Then a two-level such tree is a collection of uniform metric spaces separated by a much larger distance, and a three-level is a collection of two-level HSTs separated by a distance which is larger than the previous distance, and so forth. So these are hierarchically separated trees. Okay, so what's the question in our paper? Given the fact that we pretty much know what's happening with metrical task systems in general, we want to look at a particular parametrization of metrical task systems to see if that gives, if that parametrization gives better parameterized bounds. So the parameterization that we are looking at is the following. We want to limit the set of possible requests that the algorithm encounters, because there are many special cases where not all possible requests can be used, and the specific online problem actually can only encounter a subset of all the possible requests. So our parameterization is the number of different requests that appear in the sequence. So we will assume that the requests are drawn from a finite set of m possible requests, where m is smaller than the number of states n. And the reason why why it's interesting in this case is because when m equals n, generally the lower bounds kick in, the general lower bounds kick in. So it's interesting to see what happens when m is smaller. And the question will be, what's the competitive ratio as a function of m? So there are several motivations for this question. One of them is specific examples where there are far fewer requests than the number of states. For instance, the K-server problem is a specific manifestation of metrical task systems that has n choose k possible states, but only n possible requests. There are even more restricted versions of metrical task systems. For instance, one such example is the power management problem of Irani et al. That has, for an arbitrary n number of states, only 2 possible requests. So the sequence consists of some interleaving of these 2 possible requests. Now, another different type of motivation is the issue of leaky randomness. Randomization in online computing is generally used effectively to hide from the adversary that is generating the request sequence the exact state of the online algorithm. And the question here is, what happens if the adversary gets some information on the online algorithm, information beyond what's what the adversary can derive from the sequence itself. So what happens if the online algorithm leaks log n bits of information, adversarially chosen, per step? So one way to use that is for the adversary to hold a set of n possible requests, and then use the leaked information to choose one request among these n requests to serve next. And then the bounds might indicate what you can do with, what the adversary can do with this leaky information. So I'll survey the results that we get, and then I'll I'll show some proofs on two results, two of the results here. So the first perhaps surprising finding is that unlike the general case of metrical task systems, here, the answer actually depends on the metric space. So in particular, for uniform metric spaces, this is, in other words, one-level HSTs, it turns out that restricting the number of possible requests improves the deterministic competitive ratio. So the deterministic competitive ratio strongly depends on this number m, and the bound is upper and lower bound asymptotically is m log n over m. On the other hand, the randomized competitive ratio, which is known to be log n for uniform metric spaces already from the Borden-Linial-Sachs paper, this randomized competitive ratio does not improve even if m equals 2. So with 2 requests for randomized algorithms, the adversary can already force the randomized lower bound. Now, when you move one level higher, so when you look at 2-level HSTs, the picture is completely different. Even for 2 requests, for m equals 2, both the deterministic competitive ratio and the randomized competitive ratio do not improve at all. So they remain whatever they are for the general case. So this is somewhat surprising. Now, on the other hand, we look at a subclass of metrical task systems that is called metrical service systems, or alternatively, one can think of it as chasing subsets of the metric space. So in this particular subclass, the entries of each request, these are the service costs for the individual states, they can be either 0 or plus infinity only. So basically, each request forces the online algorithm to move to a state that has cost 0. And the states that have cost 0 are, of course, some subset of the points in the metric space. So that's why it's called subset chasing. Now here, in uniform metric spaces, both the deterministic and the randomized competitive ratio depend on m if m is small. So if m is smaller than the competitive ratio for the general case, we get a dependence on m. But there's no difference between the deterministic and randomized competitive ratio for sufficiently small m. If m is below log n. Now, the same so a similar phenomenon happens for 2-level HSTs. The competitive ratio depends only on m for sufficiently small m, but the dependence now is exponential in m rather than linear in m. And this is true both for deterministic and randomized competitive ratio. Now, this last result, the lower bound on the randomized competitive ratio, can be extended to any L-level HST where you get a tower of exponents. So for a 3-level, it will be 2 to the 2 to something that depends on n and so forth. So this is the results that we show. And now I want to show the rather simple proofs for just two of these results, not all of them. So let's start with metrical task system. I'll show the deterministic lower bound for two-level HSTs. So all the lower bounds here are existential. Their meaning is that there exists a particular two-level HST and a particular collection of two requests for which the lower bound is going to be linear in n, in the number of in the number of points of the metric space. And here is the specific two-level HST. So we have n over 2. We'll have n over 2 branches, and each branch will have 2 leaves, and we'll number these leaves. So these pairs of leaves will be indexed by 0, 0 prime, 1, 1 prime, and so forth. And they're overall n over 2 such pairs of leaves. The leaves are the states of the metric space. And the distance between 2 paired leaves is 1, and the distance between 2 unpaired leaves is a large constant c, which we can think of as c equals n. If you're interested in constants, this is not the ideal choice, but one can think of this choice here if we're only interested in asymptotics. And the two requests are r and r prime. R hits the left leaf in the pair, so the leaf that is not tagged, and all the right leaves are zeros. And the cost of the left leaf is increasing in the index, as you see here. And R prime hits the right leaf in each pair in a decreasing, so the cost there is decreasing in the index. Now we will generate the adversarial request sequence. This request sequence is partitioned into phases, and each phase is partitioned into rounds. Now, in a round, we simply hit the algorithm's position. And by that, I mean we choose the request that has positive pay in the position that the algorithm is currently occupying until the algorithm pays a cost of at least c. So this cost could be because the algorithm is moving inside a particular branch, or if the algorithm switches branches, then it automatically pays C and the round ends. A phase simply consists of n over 2 minus 1 rounds. So in a phase, the algorithm pays a total of at least C times n over 2 minus 1. Now, because a phase consists of n over 2 minus 1 rounds, and whenever the algorithm moves to a new branch, a round ends, there exists at least one branch that the algorithm never visits during the phase. So let's say the pair I prime is such a branch. This is where the adversary is going to hide for the duration of the phase. Now, in the same round, the algorithm stays at some pair JJ prime, which is different from I prime. Because whenever the algorithm moves from that branch, the round ends. So in each round in the phase, the algorithm stays in some pair JJ prime that the adversary doesn't move. The adversary will stay in the same location for the duration of this round. And the location is determined by the relation between I and j. So if I is less than j, the adversary will stay at I. And if I is bigger than j, then the adversary will stay at I prime. And the logic behind this choice is that if the adversary wants to stay in a position that would pay less than the algorithm if both of them are hit by the current request. So the algorithm will be hit by R or R prime according to if it's in J or J prime. If the adversary is at I and the algorithm is at J, they're both going to be hit, but the adversary will pay much less than the algorithm. So that's the idea. If I is less than J, and vice versa. Now, what's the cost of the adversary per phase? Well, it may have to pay C to move into I prime in the beginning of the phase. And then in each round, it may have to switch between I and I prime according to where the algorithm is. So that costs another n over 2 minus 1. And this is the total movement cost of the adversary. Then it may have to pay some service cost. But the service cost of the adversary is lower than the service cost that the algorithm has to pay. So if the algorithm pays a service cost of at most C, which is the case because the total cost of the algorithm in a round is at most C until it switches branches, if it switches branches. So it pays at most a service cost of C. The adversary will pay at most C times Cn to the minus absolute value of J minus I, because of the difference in costs that is guaranteed. Now this is of course at most C times N to the minus 1. So the total service cost of the adversary is at most 1 over N. And therefore the adversary pays a cost of at most C plus N over 2. With room to spare. And the ratio is, of course, is linear in n, so we get a lower bound which is linear in n. Now, the other proof that I want to show quickly is what happens with metrical service systems on two-level HSTs. Again, we'll show a lower bound. Here it will be a randomized lower bound on two-level HSTs. So we'll show a particular two-level HST and a particular collection of requests that forces a lower bound that is exponential in n. Now the HST will be composed of 2 to the 2 to the m over 2 minus 1 branches. So double exponential in m number of branches. Each branch will contain 2 to the m over 2 minus 1 leaves. And all of these leaves in all of the branches will have labels in the m over 2 dimensional binary cube. So the labels will be sequences of bits of length m over 2. Now the label set of a branch will be a choice. So there are 2 to the m over 2 minus 1 labels, and the label set of a branch will just choose one label from each pair of antipodal points in the binary cube. So that's why there are exactly 2 to the m over 2 minus 1 leaves, because in a branch, because each branch contains half of the points in the cube, 1 point from each pair of antipodal points. The requests will be indexed by pairs I, B. I is just a coordinate of the m over 2 binary cube, and B is a bit, either 0 or 1. And the request RIB is going to have a value of plus infinity on all the nodes, on all the leaves that have their ith coordinate equal B. And otherwise, the cost will be 0. So all the leaves whose label has the bit B in its ith coordinate are going to be hit by the requests RIB, and the other nodes are going to pay 0. We're going to construct blocks of requests as follows. So we'll pair the requests into pairs RI0, RI1. So these are requests that hit the leaves with ith label 0 and the leaves with ith label 1. So they're hitting disjoint sets of requests, of leaves, of course. And we're going to pair these requests and then choose one request from each pair for all I, and that's going to be a block. So blocks will be, so if you'll notice, such a block basically hits, if you look at all the requests in the block, they hit all the labels except for one. So there's a unique label, a unique point in the binary cube 0, 1 to the m over 2 that is not hit by the block, and that will be the block label. So each block has m over 2 requests, one request from each pair, and there are 2 to the m over 2 possible block labels. Now we're going to pair blocks into blocks that have antipodal labels. And we'll define meta blocks by picking one block from each pair of antipodal label blocks and taking all of these choices of one block per pair per pair. So overall, they're going, since there are overall 2 to the m over 2 block labels, there are 2 to the m over 2 minus 1 blocks per meta block, because for every pair we chose one of the two. And there are 2 to the m over 2 minus 1 possible meta blocks, possible choices of a block for each pair. Now we can prove the lower bound. So here is the adversary strategy. It's going to be a randomized strategy, and it's completely oblivious to what the algorithm is doing. So it's going to choose a meta block uniformly at random. Then it's going to loop through all the blocks in the meta block. And for every block, it's going to loop through the requests in that block C times. So it's going to request in sequence all the requests in the block, and it's going to iterate that for C times. And then after doing that, for the entire meta block, it's going to choose a new meta block uniformly at random and do the same thing, and that's how it operates. So here is the analysis. What's the algorithm's cost? Well, if you'll notice, the requests in a block hit basically half of the branches, meaning that if you request all the requests in the block, all of the leaves in that branch are hit at least once. So this happens for a particular block in half of the branches. Because this block is random for a now the two antipodal blocks in a pair hit complement sets of branches. Because a random meta block picks a random block in a pair, no matter where the algorithm is, it's going to have to pay at least C with probability 1/2, because it's going to pay each time we loop through the requests in the block if it stays in a branch that is hit, and the branch is hit with the branch that it begins at is hit with probability 1/2. And if it leaves that branch, it's also going to pay C. So overall, it pays a total of C times 2 to the m over 2 minus 1 with probability 1/2. I mean, the expectation is that is 1/2 of that. So it's C times 2 to the m over 2 minus 2 per meta block. That's the cost of the algorithm, regardless of the expected cost of the algorithm, regardless of the meta block, of the iteration of the adversary. Now, what's the adversary's cost? Well, if you look at a particular meta block, there is exactly one branch that is never fully hit by any block in that meta block. So the adversary is going to hide in that branch. So it has to pay, it may have to pay C to move to that branch each meta block. Then for each block in the meta block, one of the leaves of that branch is not hit by that meta block. So that's where the adversary is going to hide for that block. And it may have to move for each block in the meta block. There are 2 to the m over 2 minus 1 blocks in the meta block. So it may have to pay 1 for each of these blocks to move and hide in the specific leaf that is not hit by that block. So the total adversary cost is C plus 2 to the m over 2 minus 1. And of course, if C is very large, the ratio is going to be exponential in n. And this is the end of the proof. Finally, a few concluding remarks. This last lower bound can be lifted to deeper HSTs by considering meta-meta blocks and so forth. There are some interesting open questions here that we haven't sorted out, mostly about metrical service systems. So here are 2 of them. First of all, what happens with metrical service systems on infinite sets? So take the real line, for instance. Metrical task system bounds don't give anything because it's an infinite set of requests. But what happens if we only have 3 arbitrary sets so we only have 3 arbitrary sets that we're chasing. So they're fixed sets, but they could be arbitrary 3 sets. Can we prove any finite competitive ratio for the entire line? These sets, of course, could be infinite. One of the simplest questions that we haven't determined the competitive ratio even asymptotically or within the ballpark is think of an arbitrary weighted star metric with m requests, m possible requests. We don't know if the deterministic competitive ratio is linear in m or exponential in m. Another comment that I mentioned earlier is about leaky randomness. So the lower bound on 2-level HSTs for metrical task system that I showed uses only 2 requests. And there's a lower bound there on randomized algorithms that I didn't show. And this implies that leaking just 1 bit of information, so telling the adversary which of the 2 requests it needs to use at every step, eliminates completely the power of randomness in that particular setting. And finally, in some sense, the results here are disappointing because they don't explain why certain metrical task systems have much better than worst case competitive ratios. There is a question of, can we find better parameterization of metrical task systems that actually explains more of the of the behavior of specific online problems. And this is the end of my talk. I hope you enjoyed it, and I'll see you in the short talk of questions and answers.